Have you ever wondered how a person on the bridge of a giant cargo ship can control a 4-story tall engine with just one simple lever? I mean, we're talking about an engine powerful enough to push a mountain of steel across an entire ocean. Well, today we're going to peel back the layers on the main engine control module, the hidden brain of the ship, and find out.
Now, if you're picturing that classic scene from a movie, the captain shouting orders and yanking on a big brass telegraph, you're not entirely wrong about how it used to be. But the key thing to understand is that old telegraph was never really a control system. It was basically a glorified doorbell to signal an engineer down below. The modern system, it's the brain. It is the throttle. It has the ultimate authority.
So that really gets us to the heart of the matter, doesn't it? How on earth does this system take a simple push on a lever and turn it into massive, but perfectly controlled power, all while making sure the whole thing doesn't just tear itself apart? Let's dive in.
Okay, so first things first, we need to understand how the crew actually talks to this incredibly powerful machine. And it turns out, it's a language that's built on 100 years of tradition, but it's executed with split-second modern precision.
So this control lever isn't just some smooth slider. It clicks into place at these standardized, marked positions. It's kind of like a ladder of power. On this particular ship, you click it into dead slow ahead, and boom, you get exactly 29 RPM. Slow ahead bumps you up to 38, half ahead is 45, and full ahead gets you 66 RPM. Having these fixed points is absolutely crucial when you're trying to maneuver something the size of a skyscraper in a crowded port.
You might be wondering, why stick with these old-timey terms? Why not just punch 38 RPM into a keypad? Well, when a harbor pilot is docking this beast, there is zero room for error. Shouting slow ahead is just way faster, way clearer, and a whole lot safer than yelling out, set engine revolutions to 38 per minute, especially when things get tense.
And then, you have the panic button, emergency astern. This is a complete override. It's an order that tells the engine's brain to forget every safety rule it has about stress and strain. You are literally telling the machine, I don't care if this hurts you. I need every ounce of reverse thrust you can give me, and I need it right now.
So, that's the input, what the crew tells the engine. But what about the output? What vital signs does the machine's brain feed back to the crew?
Now, this little number here is way more important than it looks. See, unlike your car, these massive engines don't have a starter motor. They use enormous blasts of compressed air to get going. The thing is, that air is a limited resource. This gauge tells you exactly how many starts, or maybe more importantly, how many direction changes you have left in the tank.
And what happens if you mismanage this? The consequences are absolute. If you're trying to dock in a busy harbor and that gauge hits zero, that's it, game over. You've got no way to start or reverse the engine. The ship just becomes a massive, out-of-control, floating brick, drifting wherever the wind and current decide to take it.
Okay, this next feature is just brilliant. The fuel quantity gauge is so much more than a gas gauge. It's a real-time effort meter. So imagine you've got the engine set to a nice, steady 45 RPM. On a calm day, the fuel flow is predictable. But if you suddenly sail into a heavy headwind, the RPM will stay locked at 45, but you'll see the fuel quantity jump maybe 30%, because the engine is fighting so much harder. It's an incredible tool for seeing exactly how hard the engine is working.
And all of this leads to what is maybe the system's most important job of all. Not just following orders, but actively protecting the multi-million-dollar engine from the insane forces it's controlling. The system is full of these hidden guardians.
The first guardian is all about bad vibes. Literally, at certain speeds, the engine's rotation can hit the ship's natural resonance frequency. Like how a singer can shatter a wine glass? It's the same principle, but the result is a violent, shuddering vibration that could cause actual structural damage. So the system knows about this shudder zone, and it just won't let you stay there. It automatically nudges the speed up or down to keep the ship safe.
This next one is pure genius. Picture a violent storm. The ship's stern heaves up so high that the massive propeller comes completely out of the water. In that instant, all the load on the engine disappears. Without a safeguard, the engine would overspeed so fast it could literally tear itself to pieces. But the acceleration limiter sees that sudden drop in load and, in a fraction of a second, cuts the fuel, saving the engine from total disaster.
And finally, an engine this big needs to breathe. A giant turbocharger shoves huge amounts of pressurized air, or boost, into the cylinders. But if you pump in too much fuel without enough air to burn it, the engine will literally choke and stall out. So this interlock acts like the engine's lungs, making sure the air-to-fuel mix is always perfect. It simply refuses to give the engine more fuel than it can handle. But for all its intelligence, the system isn't completely autonomous, and that brings us to the crucial and sometimes pretty dangerous relationship between the human crew and this incredible machine.
This is where human error can creep in. So what happens if one tiny sensor goes bad and starts setting off a constant, super annoying alarm? Well, the crew can just silence it using the off-scan feature. The problem is, what if they forget to turn it back on? If a real disaster happens at that exact same spot, this system is now blind. It can't warn you. Checking that off-scan list is truly a life-or-death inspection.
But sometimes, the crew has to tell the machine to ignore its own survival instincts. These are the final overrides. These are the buttons you push when saving the ship and the people on it becomes way more important than saving the engine.
But here's the thing. Despite all this incredible technology, all these safeguards, and all these overrides, at the end of the day, you can never, ever escape the laws of physics. Just imagine the absolute worst-case scenario. Something is spotted dead ahead. The captain gives the most urgent command there is: emergency stop. The system slams the engine from full ahead to full astern, pushing everything to its absolute breaking point.
And even with that command, with every single piece of technology working perfectly and pushed to its limit, the whole process, from pushing the button to the ship being completely stopped in the water, can take up to 17 minutes, a staggering amount of time to be, for all practical purposes, completely out of control.
And here's why. It all comes down to a power-to-weight ratio that is almost impossible to wrap your head around. When it's fully loaded, this ship's engine has to fight against 13 tons of mass for every single horsepower it produces. It is a constant, brutal battle between precision engineering and raw physics.
Which kind of leaves us with one final thought. We've just seen this incredible hidden network of guardians that keeps this one massive system running safely. It really makes you wonder, doesn't it? What other invisible limits? What other automatic protections are quietly saving the other critical systems you rely on every single day, without you even realizing they're there?